Okay, we better make a start. The light's gone red. Let's try and remember where we were last lecture. I put this question for you to look at for homework, so I just give you the answers there. So just make sure that you get those in your own time. If you have any problem getting those, I'm sure you won't, but if you do, just email me and I'm happy to help see where you went wrong. Okay, so we started off, remember this is a slide from the last time, and we learnt that with Drude theory, we're about a factor of 2 out from the actual values, which I'll show you in the next slide. Depending on which velocity you used, you got 0.9. If you use the other velocity from kinetic gas theory, you'd get 1.1. So very similar. The important thing is it's of the order 10 to the minus 8. And as you'll see in the next slide, that's really close to the measured experimental results. So this was regarded as a big success of this very simple Drude theory. Okay? It's kind of remarkable that you actually get the right order of magnitude. So in this next slide here, you can see some of the actual values that have been measured for some elements here. And, a quick look, you can see pretty fast that they mostly begin with 2 point something. Okay, this one's a little bit larger, tungsten here, but they are all of the order 10 to the minus 8 watt ohm per Kelvin squared. Okay, so remember that Drude's prediction was about 1, and so it's off by a factor of 2, but it's still very good. Okay, so that's one of the successes of Drude theory. Just an exercise for you to do at home, just to get yourselves used to the equations that we've looked at so far. So here's the thermal conductivity of a metal is given to you. The thermal conductivity, remember that was kappa, and we had an expression for that. Find the electrical conductivity, sigma, remember, and the Lorentz number, big L, when you are given the relaxation time, tau, of 10 to the minus 14 seconds and temperature of 300. And you can assume that the density of electrons is 6 times 10 to the 28 per meter cubed. And this is kind of a typical number, so for a good conductor, so you might want to sort of have that number in your head. 10 to the 28 is sort of like per meter cubed is a good conductivity of electron densities. Okay, so I've put the answers there. I'm not going to go over them in class, and you can see if you can get those values in your own time. Okay, and I just want to say that although I've put most of the lectures up from previous year, as I go through, I might make slight changes, as some of you may have noticed already. Like, for example, I think in the slides that are already up, I probably didn't have the answers there. I would have gone over them in class. But every lecture that I give in class will go up anyway on Canvas after the lecture. So you'll get all of the notes that you see here on Canvas. But I wanted you to have all of the notes before the course so that you can see what the course involves. Okay, so we talk about now some failures of the Drude theory. With this Drude theory, we're going to talk about failures and successes. And you can, try and remember what these failures are and understand why they're failures and also the success. The success was, as I just mentioned, this Lorentz number prediction. Okay, obviously there are some serious problems with the Drude model. There has to be, right? There's no information about your particular material in there, okay? There's not even the atomic species you've got in there, not the lattice spacing or anything, so it can't be that good. Its success is really kind of lucky, if you like. It's fortuitous, okay? Now, why is it fortuitous? It's because there's some cancellation of errors, okay? Now, where are the errors, cancellation? In Drude theory, he used the specific heat as given here per electron, okay? Now, this is not necessarily a very accurate number, and in fact, for real materials, it's too large, okay? So the specific heat that he used is too large, and the velocity that he calculated using the thermal velocity of a kinetic gas is too small, okay? So these two quantities, specific heat and velocity, actually cancel out, as you'll see when you look at the equations back there. So it's largely fortuitous. It's a bit lucky. Cancellation of errors have occurred in the specific heat, which was too large, and the velocity was too small. Okay, so this obviously is not. This approach doesn't take Fermi statistics into account. Okay, and I know you've just come from statistics, so you know all about some of the statistics that we're actually going to look at in the next slides. So I know that I won't need to perhaps ponder too much on that. But we will reproduce some of the results that you've already learnt in your previous course. Okay. So let's look at another failure of the Drude model. So the other failure concerns this particular quantity here called the Peltier coefficient. Now, what is that? It's given by this symbol here, okay, large sigma, and it is the constant of proportionality between, this is the thermal current density, JQ, and this is just the electrical current density. Okay, so what he has used here for the thermal current, this is from the textbooks. I am not going to derive it, but you can read about it in the textbooks that I've referred to. The thermal current is given by a third specific heat, temperature, conduction electron density times the velocity. Okay, that's the thermal current, and we already derived the electrical current. Okay, so these are the two expressions for the current density. When you make the ratio of the two, you can get an expression for here this Peltier coefficient being equal to minus kBT Boltzmann constant times temperature over 2 times the electron charge. Okay, just substituting in for what Drude used for the specific heat. All the equations are there, so you can verify that that's what we get here. And okay, so that's a Peltier coefficient. But what is used more in studies, physics studies, experimental and theoretical, is the quantity called the Seebeck coefficient. So what's that? That's just this Peltier coefficient, but putting the T underneath. Okay, so just Peltier coefficient divided by temperature. It's called the Seebeck coefficient. Other people may know it as a thermopower. Okay, have you heard of the thermopower before? Yeah, maybe not. Anyway, it's equal to this constant of proportionality over temperature, and in Drude theory it's about 4.3 times 10 to the minus 4. Okay, but when you actually measure real materials, we find that it's about 100 times smaller in real materials. So this is another kind of failure of Drude theory. So it has some good things and has some bad things, and the good things are a little bit fortuitous, as I mentioned there, because of the specific heat and the velocity of the electrons. Okay, so obviously we want to move along a bit now and go from Drude theory into electronic properties of metals using the quantum mechanical approach. And I think you've seen some of this before. So I'll just outline some items here. So what is it called? It's basically called the Sommerfeld model, or sometimes called the free electron model. This is what we start off with. Okay. And we're going to incorporate thermostatistics in this model. So I'll introduce a little bit of that, but after a couple of slides, what I'm going to do is digress and just look a bit about the nature of bonding in solids and how the electrons actually form bands in solids. And then we'll come back to deriving the density of states and Fermi energy and Fermi vector and so on. Okay, so one important assumption here is a Born-Oppenheimer approximation, which I'll explain in the next slide probably. Some of you may know it from chemistry already. It's where we can decouple the electrons from the ions in your solid, okay? Because the electrons move really fast, and relative to the electron, the ion cores move very slowly, okay? So we decouple them and describe them separately. And we're going to just deal with one electron for the moment, okay? Keep a simple model here. And then we're going to obtain the wave function of the electrons in this very simple periodic space or material, if you like. And then we will get their eigenvalues and their eigenenergies and derive some important quantities. Okay, and when you get the eigenvalues, when you have a lot of electrons, you fill them up from the lowest energy first, okay? We'll talk about that later, because, everyone is lazy, including materials. Everything wants to go to the lowest energy, and of course, so you start filling things up with the lowest energy eigenstates for your electrons. Okay, so when you've got a solid, like a real material, we can write down here the Hamiltonian for the system. So first of all, let's just define a few things. The first term, big M, represents the mass of the ion cores, the whole of the ion cores here. Little m is the mass of the electrons. It's got a little subscript here, mass of electrons. And the first term is the kinetic energy of the ion cores. The second term is the kinetic energy of the electrons. And then we have some terms here. This term describes the ion-ion interaction between, imagine you've got this solid and it's got sort of atoms there, if you like. So we are, we're first considering the energy separately, then the interaction between the electrons and the ions. So kinetic energy, ion-ion interaction. Okay, but let's first of all look at Z and ZV. We defined that, I think, earlier on, but let's just remind ourselves. Our atom has an atomic number Z, okay? In the core, the strongly bound electrons will have the total number of electrons minus ZV, which are the valence electrons, okay, which are free to sort of move around and bond. So that's the meaning of these two quantities here. So in this term here, we have basically the number of electrons here are the ones in the core, okay? And, okay, what else? You've got the electron-electron interaction here. This is the position of the electrons, summed over all the possible electrons you've got in your system. And here we have the interaction between the ion cores and the electrons going around them. That's this final term here. So, okay, then we talk about the Born-Oppenheimer approximation, so we can make this much more simple. We do not want to have to solve this, and we cannot even now solve this exactly this equation. We can solve pretty good approximations to this using the supercomputers and get really accurate predictions of materials, but so we have to make some approximations. As I mentioned before, we use the Born-Oppenheimer approximations, which means we treat the electrons separately from the ions. okay, because the electrons are so much faster, partially due to their lower mass. So that's basically the Born-Oppenheimer approximation. So we're not going to deal with the ion cores. So a really simple model will boil down to this, which you might know from quantum mechanics here. So all we've got here, this is a Schrodinger equation for a very simple system. We have got the kinetic energy of the electrons, wave function of electrons at some position, and we have got some effective potential, which we call U, which is a potential that if you're an electron, you know, and there's other electrons everywhere, you will feel some potential due to the presence of all those other electrons. So this is what we just call U. And there's the energy of the system. And as I mentioned, we are always going to assume that our solids are periodic, not dealing with amorphous materials. So our potential is periodic, where R is the lattice vector. So what it means is the value, if you're in a unit cell here, you make your crystal up from lots of unit cells that are all the same, okay? And if you're at some origin here, and there's some vector little r here, right? And then so little r plus r will be the translation vector to the next cell. Okay, so just remember this. We're going to come back to this shortly, and we are going to solve for the wave function and get the eigenvalues and so on. But just want to go a little bit aside and talk about some aspects of how atoms behave when you bring them close together to each other. It's more kind of a qualitative description here. Okay. So if you think of a sodium atom here, and on here we're plotting the energy of its electrons, log of energy actually. Okay. So very close to the core, in the core you'll have the 1s electrons level, they have some energy. Then you'll go further out from the core to the less bound electrons, other 2s electrons, and then you'll have the 3 types of p electrons, and again the 3s, the very outermost electronic orbital of your sodium atom. So this electron is actually really quite loosely bonded and quite easily bonds to other atoms because it's not very happy on the sodium, it's all by itself. Okay, so, you know, in each energy level you can have 2 electrons occupied with spin up and spin down. And, you know, you have your 11 electrons organized like that, okay? So if you, okay, we've just considered 2 sodium atoms for a start, like a big separation. There's your one sodium atom and there's your other sodium atom. And we're just going to focus on the outermost electrons. As I mentioned, these are the ones that are free to move around and make bonds with other atoms in this system. These are tightly bound electrons and they don't really interact very much with each other. So just looking at those ones, and then we're going to consider, you know, when you bring them closer together, you're going to get energy bands forming. Okay, so let's just look a little bit more here. Okay, so when you start bringing these are the outermost electrons. Remember the 3s electrons. Here's one sodium atom. Here's another sodium atom. But then you bring them together, and what happens is you get new states forming, a bonding state and an anti-bonding state, because they have been brought together and their wave functions are interacting, and they form bonding and anti-bonding. And both of these electrons will want to occupy the lower energy state, one spin up and one spin down. So now we want to think, okay, that's a molecule. What about a solid when you've got, you know, hundreds of these sodium atoms all coming together? what happens is your energy diagram starts to look a bit like this, okay? Let me just explain. A is a separation, so that when the separation is really big, you just have the position of the isolated 3s electron of the sodium atom. Remember, we're only considering the outermost ones. And now as you bring them closer together, the A gets smaller, okay, gets smaller, going along here, and there will be some optimum value of A that corresponds to the lattice constant of bulk sodium, okay? So at the minimum energy here, this is where the crystal will form. And as you saw before, there'll be some bonding state and some anti-bonding states form. But it's kind of, you've got to imagine when you've got millions of them, these discrete bands will become broadened. So this kind of indicates the way they become broadened, because you've got not just one sodium atom interacting with another one, but you've got this sodium atom interacting with one over there, one over there, and one over there. Okay? And every sodium atom will have their different kinds of interactions. So basically, this is what you will end up. It's called an energy band. Okay? And so bands of levels, energy bands, we'll come back to those, of course, very soon in the lecture course. We'll be talking about energy bands and so on. This is just kind of introducing it. And every band, we can put, as I said, 2 electrons in one band. So for all of the bands that have been formed by bringing all these sodium atoms together, all of the N bands, N over 2 of them will be filled. Okay? So the red part indicates the bands that will be filled with electrons, and there'll be some extra bands that have formed that are unoccupied and don't have electrons in. Okay? So these will be basically the conduction bands. Okay? And the Fermi level is the energy of the uppermost energy level that's got an electron in it. So you can see, if you draw it this way, that sodium is metallic, because at this point here, just a little bit lower energy, you've got all filled electrons, and just the next level up is empty. So the electrons can easily conduct. They can easily jump up to the conduction band and move around in the crystal. Okay, just another example. So this is a metal, and this is kind of typical behavior for sort of metals. You get this continuum of bands where the Fermi energy will cut the bands, and there'll be immediately above the Fermi energy there'll be an unoccupied state, so the electrons can be highly conductive. You might guess what we're talking about now. Semiconductor. Okay, the main thing is we have the introduction of a band gap. So here is an example of silicon or diamond. Now, in a silicon or diamond atom, there is 4 valence electrons. Okay, it's got some core electrons, but it's got 4 in the outer shells, 3s and 3p, and they can make very strong bonds with other atoms in the system. Now, when we do look at the sort of various crystal structures that can form, we will see what actually the structure is of silicon or diamond. But just let me tell you, in the repeating cell, to make up your bulk, it's got 2 atoms in what we call the unit cell. And there are 8 states per atom and 16 states per cell, which I'll show you on the next slide. But okay, what's the point? The point is, okay, we've got the same diagram before as we had for sodium. Say over here, you've got separated silicon or carbon atoms, and you can see the discrete nature of the energy levels of the sort of like free atom of silicon or free atom of carbon. And then as you bring them closer together, these states start to interact with each other and broaden, okay? And as you eventually keep bringing them together, you will hit a minimum in energy, and that's where the structure will want to form at this value of lattice constant. Okay? So when you are at the equilibrium geometry of your silicon or carbon here, you can see that there is a so-called band gap that is formed between this shaded region is the states that are occupied by the electrons. Then there'll be a band gap where no electrons are allowed. And then up here, there's your conduction band. Okay? So, yeah, it's very important to understand the idea of, we'll get to it later as well, metallic materials, semiconducting materials, and insulators. Insulators are very much like these here, okay, except the band gap is much larger. Just a little bit more detail, what's behind those bands that I just showed here. This is a little bit more detail. In the single atom, there's there is the 1, 2, 3, 4 electrons of the isolated atom. Now, in silicon or in diamond, what actually happens is that the S and the P electrons already hybridize with each other, and they form what you call sp kind of bonding. And this is where the 4 electrons are occupied in these kind of sp bonds. Okay? Now, when you bring, say, 2 or more atoms together, you will get again the formation of bonding and anti-bonding states up here. And say if this is the case, you've got 2 silicon or 2 carbon atoms that have 4 valence electrons, 4 from each atom. They will arrange themselves in the lowest energy possible way, and that's start filling up from the bottom. Spin up, spin down, spin up, spin down, spin up, spin down, spin up, spin down. Big band gap, and then these will all be empty. It's called the valence band. It's called the conduction band. Don't worry about the dangling bond state. If there is a defect where one of the bonds, one of the atoms, say, can't find another partner to bond with, then it will just create what we call a dangling bond, and it will just hang there sort of with only 1 electron in, and forming the band gap there. This is very important for defect engineering, as we'll learn later on. I think lecture 15 or something like that. Okay, so now we're coming back to, the quantum mechanical description of a very simple material, if you like. The next slide here. Yeah. Okay, so for those of you that have Ashcroft and Merman, you can read about it in more detail than I can give here, chapter 2. Also in that Oxford book, I'm going to encourage you to look at that Oxford book. It's really easy to read. It's not very thick. It's got quite a lot of the material I'm presenting here, and it has words that describe very nicely sort of the equations and so on. And as I said before, it also has these funny anecdotes and explanations that are not usually in a textbook. Okay, so what were you doing now? Okay, particle in a box. Okay, there's our box. What we're going to do is just get rid of this potential. We're going to keep the periodicity, but this potential, such as that, it's just basically a constant offset. So we are not going to even consider that. So this will go to 0. And then we are just left with boundary conditions. We still have atoms everywhere, and this will make it possible to solve our equations. Okay, so let's have a look here. This is called the free electron gas, or the Sommerfeld model here. So let's define a few things. We are going to consider capital N electrons, okay, and these N electrons are confined to some square box here of cube side length L. Okay, we are just dealing with one electron here, and the one electron has a wave function psi as usual. And okay, there is our nice simple Schrödinger equation here, and we have boundary conditions on our wave function. You know, as I explained before, it's periodic. Every wave function at position r is equal to okay, x, y, z, three-dimensional. If we go to the next unit cell in the x direction by L, which is the repeating unit, it's just exactly the same. Okay. Same for the y and z directions. Okay, this basically shows the same thing, I think, except here. Okay, this kind of illustrates our solid. Okay, it's periodic. Got a star, circle, circle, star, circle, circle, star, circle, circle. Okay, this is our crystal that we're making up with the periodic boundary conditions. And as you'll know from quantum mechanics, the solution, psi, is equal to 1 over the volume here, normalized to the volume, e to the ik dot r. Okay? R is the position vector, and k is the wave vector. So here, this is what we have already. You can plot here the energy of your electrons here, h bar squared k squared on 2me. That's just momentum squared on 2me. You can write your k vector in terms of its x, y, z components here, and the k vector is 2 pi n, where n is an integer, over L. Okay, so this is very important. K equals 2 pi n over L. These are just numbers, integers. And so you can write your free electron energy as h bar squared on 2me. Instead of k, we've got the 2 pi over L squared, n squared. And to get a feel for that, and you probably know very well in any case, you get your free electron-like parabola. Okay? So what we've done here is just plotted in one dimension. N, y, and z are 0. So we are not considering that. We're just plotting this function here for various values of n, x. Okay? So this is n along here, given by this expression here. And there's the resulting energy. Okay, now, I know you've done this in statistical mechanics, but this is probably presented in a little bit different way, what we're doing here. So just remember, this is a one-dimensional, it's a parabola, and you've got discrete energies corresponding to the various n, okay? Now, imagine you're kind of up here with your eyeball looking down on that, and also in the y direction, nx and ny. What you'll see is the grid of endpoints. Okay, it's obviously in 3 dimensions because you've got an nz as well. Okay, so it's a sphere, and we're just cutting through the sphere and looking at those ends. And what that really corresponds to is a surface of energy. Okay, because remember, we had here, this is the energy, and k depends, on n. You put n equals 1, you'll just get the point at the middle. So this corresponds to the outside of a circle. You can define some n max will correspond to have a corresponding energy. Okay, so that's your grid of endpoints looking down. Correspondingly, k points, you can plot a grid of k points because look here, here's your k grid. If n equals 1, you'll get some value of k. N equals 2, you'll get some value of k, and so on. You can make a corresponding grid of k points. Okay? And this is what we call k-space, reciprocal space, wave vector space, I don't know what else you call it. Just looking down in 2 dimensions at the moment. Now, you know that for every K point, which corresponds to particular energy level, it can have 2 electrons in. Okay? So one of these K points can have 2 electrons. So remember, we have N electrons, big N electrons in our system. So we've got N electrons, and these N electrons are going to be distributed on N divided by 2 K points, because every K point can have, 2 electrons in the spin up and spin down. Okay, and remember, cutting through, say here, it was a parabola. So the lowest energy will be the one in the center here. So we have to fill up. What we're wanting to do is to work out basically how many electrons can we fill this sphere up to, given that we've got N electrons and each K point can house 2 electrons. So you start with the lowest energy. This is where your electrons will go, and you will keep filling up the lowest energy reciprocal lattice points or wave functions, whatever you want to call them, with energies at the lowest point. Okay? And it might go out depending on how many electrons you've got. Now we're coming to an important point here. Okay, we're getting there. So basically, okay, so we need to determine, say, an N max, which is just, you can think of that as the radius of a sphere. We want to determine N max where we have filled up all of our electrons. Like, is this enough points to have our N electrons filled up, or is it here? What is the value of N max that we need to have to fill up our to occupy our electrons? Okay. So what we know, this is the important thing here. Okay. We know this is a sphere. Okay. This is a sphere just cut through the middle. We know it's in 3 dimensions. We know the equation of a sphere: 4/3 pi r squared. And in our case, we have 4/3 pi N max squared. Okay, that's just our variable. And we know that we want to have inside that sphere N over 2 electrons, or N points. Because when we have N over 2 points enclosed in our sphere, we can occupy our N electrons. Okay, did you get that? I hope you get that. If you don't get that, just come and ask me. Okay, we only need N over 2 points to be contained in our sphere, because each point can have spin up and spin down electrons. So we don't need N of them, we only need N on 2. And when you rearrange that equation here, you can find that N max is equal to 3 times the number of electrons divided by 8 pi to the power 1/3. That's just rearranging this equation, which we got from just the volume of a sphere. Okay? And, okay, so this is important. I should perhaps put a red box around it, but we're going to make use of it in the next slide anyway. This is, you've just seen before. Okay, this is just, okay, we had an expression for the energy of the electrons. Here we've just put max on, okay, to say that at this point here, this is the maximum energy. It's got the maximum K point. And the maximum K point is given by 2 pi L over N max, which we now know. So a little bit confusing, or maybe it's obvious. Depends how your brain works. I'm not too sure. I find it a little bit confusing, but in a way it's a much more visual way of arriving at what we want to arrive at. Okay, it's all the same. We derived that N max, our maximum sort of N radius, if you like, was equal to that. we know the electron density is defined by number of electrons divided by the volume, which is L squared. What you are going to do, or what you should do, is basically try and derive this expression, okay? All you have to do is stick this Nmax, which we just derived, into there, okay? And you will get this. It might take you two or three, minutes of thinking, but you'll get it. Okay, so we derived that. We know that. Stick that in there. You'll get this expression here. This is an important expression. This is the expression for the Fermi energy, h bar squared over 2m, 3 pi squared n to the power 2/3. And lots of physics is sort of determined by the Fermi energy, and has a corresponding Fermi surface, which is the surface in 3 dimensions that is made by locating the Fermi surface, like in the Fermi energy in every direction in your crystal. And the corresponding K max that corresponds to the Fermi energy is called the Fermi wave vector. Okay? And then we can also have the Fermi velocity, Fermi momentum, and other things. This equation you should recognize from your stat map. You will have seen that, yeah. I think you did a different way. You integrated over 1/8 of a sphere or something like that. But it's the same thing. Okay, this is just a little problem for you. I know it's probably extremely easy. All you have to do is substitute in the density n of electrons into that expression that we just derived at to calculate the Fermi energy. But all of this, just do it. It's good exercise. Gets you used to the equations and also the physics of what's going on. So let's have a look at some values of the Fermi energy. Yes, some of you will notice that we had aluminium, but maybe it's not exactly the same density, so this might be a different... I don't actually know what the value of on that problem is yet, but it might be 11.6 or it might be slightly different. Okay, so the Fermi energy is quite a large energy. Well, for sodium it's 3.2, copper 7, aluminium 11-ish. And these are kind of typical energies of the binding energy of atoms in these materials as well. With the binding energy being, okay, you've got a chunk of metal, sodium, copper, aluminium, and you pull it apart so that every atom in your solid is now separate. Per atom is the binding energy. And they are kind of the similar order of magnitude. Order of magnitude, not value. Okay. So we're going to go on a little bit, and again, you will have seen this thing from StatMech, I think. Okay, Fermi-Dirac distribution. We're going to look at the Fermi velocity, the density of states of free electrons, and talk about the Fermi-Dirac distribution briefly. Okay. So the Fermi velocity, speed of electrons at the Fermi level, which is sort of obvious, I guess. Kinetic energy, half mv squared of the Fermi velocity is equal to EF. And remember, we have an expression now for the Fermi energy that we derived. And so it's straightforward to get the Fermi velocity like that. Okay? And as you can see, to a first order, it actually doesn't, it's independent of temperature. It's only dependent on, really, the electron density. Okay. So, let's have a look at some typical values of the Fermi velocity. Again, sodium, aluminium, and copper. We had already the Fermi energy. Corresponding Fermi velocities, 1 times 10 to the 6 meters per second for sodium, aluminium a bit larger, and copper a bit smaller. but you can see they are all of the order 10 to the 6. And what do we notice? It's bigger than Drude, right? It's bigger than Drude. So this is good. This Sommerfeld model is already getting us velocities bigger than Drude. Remember, Drudes were too small. So this is another important point to remember. Sommerfeld model, or free electron-like model, your Fermi velocities are more realistic in this description. But still, it's a fairly simple model, right? We've got to keep that in mind. But it's improved on Drude. Okay. Now we want to derive an expression for density states of free electrons. Of course, the important equation here is in blue. So what have we got? Remember before we had derived, well, we had derived specifically sort of at the Fermi level, but you can, this is your, remember before we had EF, the Fermi energy, given by this nice equation to the 2/3 that we had derived. Instead of writing it in terms of the electron density, little n, we've just put it back to being the total number of electrons per volume in this equation here. And we are just generalizing it to any energy. It doesn't have to be at the Fermi energy, okay? It can be smaller down near the bottom of the circle. Remember, our Fermi energy was at the maximally filled situation. So you can rearrange this expression here to put it in terms of n instead of e, and you will get this expression here. So this tells you the number of electrons at a particular energy. And here you can write it in terms of the density of states. So this tells, what is the density of states? It's G, we denote it by G, and it tells you at a particular energy. You can also integrate it to find how many electrons in a particular, this is energy along here, okay? So if you're a particular energy EA, say, let's say EA is here, then you can just read off what your value of G will be, okay? Tells how many states fall in a certain energy interval. And this is really getting towards real, remember this kind of plot, remember this density of states, we're going to do a bit more later on, but you've got here density of states, how many electrons, if you like, are present in the solid at what energy. And this is your characteristic shape for a free electron-like material, like aluminium or so. A real material, you'll see later on, has lots of bumps and interesting features in it. How much time do we have? Let me see. Okay, I'll leave it with a problem for you. Okay. So how are the electronic states populated at finite temperature? Yeah, I think we might just leave it here because this is leading us into Fermi-Dirac statistics, and there's a couple of slides on that, so I don't really want to start that kind of new topic here. I mean, I'll just show you what comes next. You know, you will recognize that, okay? It's a Fermi, we're going to have the Fermi function and so on, but that's at 0 temperature. So I think I'll leave it here for now. Thank you. I just want to say also, I'll try and put assignment number 1 towards the end of next week so that you have it and you can look at it over the study vacation. Might be good. Yeah, sure.
Okay, cool. So when we said that this expression,
yes.
You said that because this is our parabola, right?
Correct.
And we see the parabola like that?
Yes.
So we have a sphere.
Yeah.
And you said that we had n onto for example, K points, because
Right.
for each K you have two spin up, spin downs, or an electron and two.
Yeah, yeah.
So okay, but so we consider only those states, but don't we have to like? Is there any? You know what I mean?
Yeah. That is kind of actually what I'm trying to plot there. We're just looking at the N. So let me see if I can. Yeah. So this is actually the energy that's being plotted here. So when we're looking with our eyeball down on here, I'm just kind of looking at the N values. So I'm just plotting the grid.
Okay.
Yeah.
Yeah.
So there'll
Okay.
be.
Oh, so yeah, you just have the surface like of the parabola.
Yeah. Yeah.
Yeah. Okay.
So just forget about the energy for the moment. In these diagrams, just think of them
Okay.
as these ends here.
Perfect. And I have another question.
Okay.
I wasn't there last time because I had a field trip with
Yeah.
my other class, and at one moment in the slide you said that the Drude theory doesn't have the right sign for E when it comes to
Right.
the all risk
Yeah.
stuff
Yeah.
coefficients.
Yeah.
But I
Yeah.
didn't get it fully.
The point of that is Drude theory only considers electrons.
Okay.
Right?
Yeah.
Now, those positive numbers that we had measured in that table
Yeah.
were positive because they were due to electron conductivity of holes. So they had a different sign.
Yeah.
Okay? Because those values that I gave were actual measurements, and because basically Drude only has electrons, it didn't consider holes in Drude theory.
Yeah.
Yeah, so it couldn't possibly get the negative sign.
Yeah. Sure.
Yeah, because
Because yeah, you had RH, it was -1 up to NE. So my
Yes.
question that was for Drude theory, you have only electrons. So
Yep.
this will be negative. So
Yep.
what's the point of comparing all the whole effect to the Drude model? Like, you know, like because E it's like kind of fixed for Drude theory because it's only electron.
yeah.
So why could we get a wrong sign for E because of the all coefficients? This was my question.
Yeah.
I don't see the link between the two.
Okay.
Like,
Yeah. So because Drude only considers electrons, he can only ever predict values, positive values of R.
yeah,
Okay.
yeah,
And so that when experimentalists measure, they were getting, a long time ago,
Yeah.
they were getting positive values. And at that time, everybody only knew about electrons.
yeah.
So they were very puzzled why we're getting some negative values. And his model, of course, couldn't explain
Yeah.
that. That's the only thing.
So why would they didn't know about positive?
Yeah.
Okay. They
So it's
didn't know about-
puzzling at the
Yeah,
time.
okay. I didn't get it. I was like,
Yeah, it's hard.
electron is negative, so how could they? Okay, they didn't know about the positive.
Yeah.